Hi guys, today I'm going to be explaining how to make an FRC style gearbox for a first robotics competition drivetrain. Alright, I think the best way to understand how to go about making this gearbox is to first take a look at an example. Now, in this example, you can see that we have two motors in the back connected to a set of gears in the middle. Now, the reason that we have the motors connecting to a set of gears is so you have more control over the speed of your drivetrain, and so there's more torque. That torque will be able to, 1, move the weight of your own robot, as well as pushing other robots. Now, this set of gears is connected in a way that there's two stages. Our first stage is going to be connected from here to here, and our second stage is going to be the gear set here and here. In order to assemble this gearbox, the first step we have to take is making the front and back plates. The front and back plates are going to define the mounting holes for our motors, where our output shafts are, and where our gears sit. In order to begin making these plates, we need to figure out what gears we're going to be using at what reduction. So we're going to begin this by going ahead and opening up the JVN Design Calculator. Now, the JVN Design Calculator is going to help us figure out what numbers we need to get the speed we want. So near the bottom, you'll see we have a lot of options. Today we'll be focusing on making a custom 1-speed drive. So go ahead and go to custom 1-speed drive. You'll notice that these are the options we have here. Now, for the top box, you should have exactly the same amount of information I have. All of the numbers should match up. We will be putting 2 gearboxes in our drivetrain, 2 motors per gearbox. The total weight of our robot is going to be 154 pounds. This accounts for the 120 pound limit for the robot itself, as well as the maximum of 34 pounds for the bumpers. Our wheel diameter for this drivetrain is going to be 4 inches. Now, as you can see here, we have a set of driving gears and a set of driven gears. Already I've inputted a few numbers from a previously made gearbox. Over here it gives us our output. Our drivetrain free speed is going to be 14.54 feet per second, and our drivetrain adjusted speed will be 11.77 feet per second. The drivetrain adjusted speed, I would not really trust that number, as it's kind of arbitrary in the sense that you don't know what coefficient is going into adjusting it. For example, you don't know how the carpet is going to act at all times. So for now, we'll be focusing on the free speed. That will tell us the most about how fast our drivetrain is going to go. Over here, we have our pushing, or current draw per motor. And you can see it's 83.11 amps right now. You want to keep it at around 80 amps per motor. That's the safest range for drivetrains. Alright, so let's get started into inputting our gears. As you can see, I've only used up the first 4 boxes, each one representing a gear. Our first one is going to represent the gear that goes on our motor. Over here in the CAD, you can see that this motor is connected to this 12-tooth gear. So what we're going to do is, we're going to go to the VexPro website, Motion, Gears. Near the bottom, you'll see that there's an option for Sim Motor Gears. We're going to click on this. These are all the options VexPro provides. So they provide an 11-tooth, 12-tooth, aluminum and steel, 13 and 14-tooth steel spur gears. For now, we're going to be using the 12-tooth steel spur gear, as this is the standard we've been using on our team for a while. So the first number is going to be 12. Now, the second number is going to be our driven gear. So this 12-tooth gear here is going to be driving this gear over here. As you can see, I've inputted 48 teeth. Now, I know that 48 tooth gears exist by going to the VexPro site. Again, you can take a look at the options they have. We'll be looking at the 20 DP half-inch hex bore gears. And all of the options, you can see that the 48 tooth aluminum spur gear does in fact exist right here. So that is the number I've inputted. Now let's say I was aiming for a drivetrain free speed of 16 feet per second. Now, thinking about this logically, in order to increase the speed of my drivetrain, my driven gear is going to have to decrease in number. The driven gear has to decrease. So I can change this to 46, and you'll see that the drivetrain free speed should increase. And it has increased to 15.17. I'll decrease it again, and again, until it reaches a desired amount. So right now, you can see that if I change it between 44 and 42, I'm fluctuating between 15.8 and 16.6, but I want to get closer to 16. In that situation, I'm going to have to change the other numbers in order to get it more precise. The reason I changed it in increments of 2 is because, as you can see on the website, all of the gear teeth typically change in increments of 2. Sometimes they will jump from 2 to 4 increments just because of their availability of gears. So in order to decrease my speed from 16.6 to closer to 16, I can increase the driving gear. So if I want to, this will allow me more control over this. Sorry, my mistake. You will not be increasing the driving gear, you'll be decreasing it in order to decrease the free speed. If you wanted to decrease the free speed by altering the driven gear section, you would have to increase the number. So from 32, I believe, I'll be decreasing it down to 28. Now I'm getting much closer to 16. Let's kick it back up to 30. And I'm at 16.61. So essentially what I'll be doing is adjusting the numbers until I get my desired free speed. And I'll constantly be checking these numbers with the gears that VexPro provides to make sure that these gears can actually be bought and used. So let's adjust this 48 and increase it a little bit. There we go. That's close to my drivetrain free speed of 16 feet per second. Alright, now I have all my numbers set up. Let's get started on making the layout sketch for the gearbox. So I'm going to go ahead, open Autodesk Inventor, and start a new part. The first thing we're going to start with is our 12-tooth gear. Now you'll notice that on Vex websites, they provide both 20 DP gears and 32 DP gears. Right here, 32 DP gears. Now, DP refers to the diametral pitch, which is essentially the amount of teeth per inch on the gear. 32 DP indicates there'll be more teeth per inch versus a 20 DP gear. So when I'm making my layout sketch, I want to make the layout sketch showing how the gears connect. If I open up any drawing of any gear on VexPro's website, right here, it'll give you a few different numbers. It gives you the outer diameter and the pitch diameter. The pitch diameter refers to where the teeth mesh. Let's take a look at the numbers in the table. The tooth count is 14 and the pitch diameter is 0.7. Over here, the tooth count is 32 and the pitch diameter is 1.6. You can clearly see that in order to achieve the pitch diameter, they have divided the tooth count by 20, which is in fact the diametral pitch right here. So when we're in Autodesk Inventor and we're illustrating the gearbox layout sketch, we're going to start by doing 12 divided by 20. The 12 indicates the number of teeth on the gear and the 20 indicates the diametral pitch. This will in turn give us the overall this will give us the overall pitch diameter for the gear. Now, right now we're going to make this gear in construction. The reason we're putting this in construction is because this is not going to be a final product of the plate. This will not make a hole or anything. This is just representing where the gear is going to be located. Alright, we know there's going to be 2 motors on our gearbox, so let's add another one on the x-axis. This one can also be set in construction. Alright, now that we've made 2 of our gears, let's get on to the second gear. Our second gear is going to be this 42-tooth gear. As you can see in this example gearbox, these two are going to connect in this fashion. For now, I am not going to make the gear on the x-axis because Autodesk Inventor will cause it to lock automatically. I'll be making it slightly above. So I'm going to take the number of teeth again and divide by 20. Let's put this in construction. Alright, now we know that these are the first set of gears we'll be using. Since these are showing the pitch diameters, we can make them tangent because that's where the gears are going to mesh. Alright, the next thing we need to do is make our next set of gears. Now in this example, you can see that the next gear is on the same shaft as the first gear. Just following the set of gears, you can see how this would work. These two are at a 1-to-1 ratio. Essentially, this gear is traveling at the same speed as this gear. And then this causes a reduction on the bottom shaft when it interacts with this gear. In our JVN Design Calculator, we can see that our third gear is going to be a 30-tooth gear. So back to our drawing. I'm going to make a 32-tooth gear right on top of this one. Construction, once again. And that's the beginning of our second stage. Now the last gear that we need is this 50-tooth driven gear. This 50-tooth driven gear is going to be on a different shaft entirely, as shown by this gearbox. It's going to be on the bottom shaft. So, somewhere, just make an arbitrary circle that's 50 divided by 20. Construction, once again. This gear is going to be connected to this gear, so we can make these two tangent. Alright, now you can see that Inventor has made these gears yellow as to illustrate that they're not fully constrained. Let's add a few constraints to them. We want the gearbox to be pretty symmetrical, so we can connect these two gears with a straight line in construction and make it perfectly vertical. Alright, now you can see that this gear is wanting to move around as well. Let's connect it to the gear at the origin. And for me, it's made it perfectly horizontal automatically, but if you need to, you can use the horizontal constraint right here. Alright, let's take a look at what else is moving. This gear is still moving up and down. Alright, before we add more constraints to it, let's add a few different items to our gearbox. First, let's outline the first motor. For sim motors, the outer diameter is going to be 2.54. But in order to adjust for tolerances, we'll be changing this number to 2.56. If you want to confirm this number, you can go to the VexPro website, Motors and Electronics, Sim Motor, just scroll down to the drawing. Alright, right here you can see that the outer diameter of the motor is 2.52, I believe. Alright, 2.52, right here. So I increased it by 0.04, which will be more than enough to adjust for tolerances and space when mounting. Alright, now that these have been adjusted for tolerances, let's make this gearbox as compact as possible. Let's make this motor tangent to this one. Now, since these motors are not representing anything on our gearbox plate, we can make them in construction. Alright, now that we've got the overall layout for our gearbox, and all of our items are in blue, indicating they're fully constrained, we can go about creating mounting holes for everything. So the first setting mounting holes we can focus on is the motor. On Vex's website, you can clearly see that the bolt circle is a 2-inch circle, and that our bolt holes are for 1032 bolts. So let's go ahead and make a 2-inch bolt circle on each of the motors and put them in construction. Alright, now we need to add the bolt holes themselves. In order to ensure that they're perfectly 180 degrees apart, we'll be using the circular pattern tool. I'm going to be making it 4 holes just in case we need to adjust the motors for some reason during mounting. Same thing applies to the other side. The bolt hole is 3/16, indicating a number 10 bolt. And we'll be circular patterning this around. Alright. The circles right now are in green, indicating they're not fully constrained. I'll be constraining them to show that they're going to be perfectly aligned. You may want to leave them moving around for later adjustment, but for now this will be what I'm doing. Alright. The next hole we need to add is the hole that allows the hub of the motor to enter the plate. This hub can be seen in this drawing right here. This hub, as detailed by the drawing, is 0.75 inches in diameter. So when we make it on our gearbox plate, to adjust for tolerances once again, we're going to make it 0.76. Alright, the next thing we need to make is the bearing hole on our top gear. Bearings are all 1.125 inches for flange gearbox bearings, 1.125. Now, thank God we made the drawing first. We can clearly see that the mounting hole here is interfering with the bearing here. This is perfectly okay since we've already used these 2 bolt holes. When we mount it, we can see that we'll be using these 2 versus these 2. Since we know that, let's adjust the mounting holes to make them more concise. I'll be deleting the pattern, delete pattern, deleting the line, and moving the mounting holes so they're perfectly vertical with each other. Let's circular pattern this. And this one. For now, I will actually leave them unconstrained as to allow for any later adjustment I may need to make to the mounting holes. Alright, now we've had our top bearing hole made, our holes for the hubs. Now we need to make the bottom one. The bottom one will also be a 1.125 inch bearing hole. The last thing we need to make is how this gearbox mounts to the drivetrain. In order to standardize any mounting we do on our team, we'll be using a 1.875 inch bolt hole in construction and put 3/16 bolt holes on the sides. These will be perfectly 180 degrees around. In a video later, I'll be explaining how these bolt holes also interact with the bearing block we'll be putting in. The bearing block refers to this piece right here. Alright. The last thing we need to make on our gearbox is our standoffs. Our standoffs is what separate the front plate, right here, from the back plate here. You can see in this situation we've used Thunder hex shafts in order to make our standoffs. So our standoffs in our drawing, we can place one here, 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 and here. Let's go about doing that. The first thing we need to know is that the hole in our standoffs is going to be 0.25 inches. Now, we cannot just place the hole over here, because you can clearly see if the hole was there, the standoff would run into our gears. In order to adjust for this, we'll be making the outside of the standoff. The outside of a standoff is going to be 0.6 inches in diameter. In order to illustrate where I got this number from, let me give you a quick demonstration. A Thunder hex shaft is 0.5 inches in width. If I put a circle over this shaft, you can see that going from corner to corner gives me 0.577 inches. Correct? So what we're going to do is make a circle around this at 0.6 inches, again leaving room for tolerances. Now we can make the 0.6-inch circle in construction and make them tangent with the objects that are already inside our gearbox. Let's repeat this process 3 more times. The reason we use a 0.25-inch hole in the middle is because we will be using 1/4-20 bolts to secure our standoffs. Now the one thing that we need to ensure is that our gearbox standoffs do not interfere with the chain that will be running around transmitting power to our other wheels. Now right now I can make this outside circle tangent to the motor and gear here. If I do that, you can clearly see that if chain were to run from here to here and here to here, it would go around the standoff. In some situations when making the gearbox, this is not possible. So instead of making it tangent to the motor and gear, you will have to adjust it, just so the chain does not hit the standoffs. For now, we got lucky, and the chain passes smoothly around it. Besides this, there are no other mounting holes we need for our gearbox. All of these other holes that you see in our plate are called pockets or lightning holes. These holes will essentially just reduce the weight and while still providing a sturdy structure. Alright, the final thing we need to do is create the border of our gearbox. So the border of the gearbox will keep everything in and actually give us the plate itself. Right now you can see that the motor holes are still unconstrained, so let's go ahead and straighten these out. I'm connecting them with the line, putting the line in construction, and making it perfectly vertical. Alright, we now have the overall layout of our gearbox. Let's add a border. The border will be created by connecting lines and arcs. The lines will be made tangent to the outside pieces, and I'll be using the coincidence constraint here to connect it from the edge of the line all the way to tangent to the circle. I'll be repeating this process for every line segment and every circle. Alright, now that I've made all of the lines connecting the pieces, I'll be filling in these gaps with arcs. Go to Arc, Arc Center Point, go to the center point of the arc, drag it out, and connect the segments like this. Always look for that green dot indicating you've securely selected that center point and those endpoints. Fantastic. Now before we extrude this gearbox, I want to show you why making a layout sketch like this is so beneficial. Let's say we go to our JVN Design Calculator and we decide to change some number. Let's say we want to decrease our speed from 16 feet per second to 14 feet per second. So we adjust the numbers around a little bit. It looks like this now. What we can do is we can go back into our sketch. I can change my 42 tooth gear, which happens to be this one. Double click on the number, change 42 to 48, indicating a 48 tooth gear. Press enter. Voila. The gearbox automatically adjusts. The only thing you will have to do on your own is fill in the little gaps on the edges. But besides that, everything fits perfectly now. Let me just undo that real quick. Now let's finish the sketch and extrude our plate. Alright, now this is an issue that seems to come up a lot with students. This issue occurs because Autodesk Inventor is indicating that this is not a closed loop. Somewhere in the outside there is a gap. Let's diagnose this. We're going to right click on our sketch. We're going to look at we're going to edit the sketch first, I believe. Right click, Sketch Doctor, Diagnose Sketch. We'll be diagnosing open loops. Press OK. And right there, it's showing us that there is an open loop. Let's click Next. Open loop is in this profile, etc., etc., etc. Let's click Next. Close the loop. Finish. Let's just say yes. Successfully closed. Click OK. Alright, now that point that was open before should be successfully closed. Finish the sketch. Extrude. And now we have a plate. We will be using a 1/4 inch metal, so 0.25. Congratulations! You've now made a gearbox plate, which we can later implement in making this gearbox. Look forward to another video illustrating how this plate comes together to make the gearbox. Thank you.